So I think we are ready to start. It's a pleasure for me to introduce David Sobral, who is visiting this week CXC for a collaboration project with me and my group. David is a professor at the University of Lancaster, astrophysics professor at the University of Lancaster in the UK, and originally he's from Portugal, and this is where he did his undergrad studies, and then he started to move around Europe a little bit. He did his PhD in Edinburgh, and then went back for a postdoc in Portugal, and then also he was for a long time a postdoctoral fellow in Leiden, in the Netherlands. And he's extremely successful astrophysicist. He has a great record of accepted observing proposals. I think I counted like 30 as a PI and many more as a CLI. And he has been devoting a very long time in understanding and exploring the early universe. And this is what he's going to tell us about today. And if you want to talk with him, he's going to be around until Friday, and we're going to go out for dinner tonight. So let me know if you want to join. And so it's going to tell us about exploring the early universe with the largest emission line surveys from redshift 2 to 8. Thank you.
Thank you all for coming. Thanks, Francesca, for inviting me. It's the first time I'm here, so I'm having a really great time before I start teaching, and then I do nothing else. Now, today I'd like to talk about some of the research that we've been doing over the last few years, and specifically targeting emission line galaxies, and we'll see why. And I guess the major motivation, to put it as simply as possible, and I guess many of us were interested in doing, is to try to understand how the hell did the universe went from something that was incredibly simple, that we could probably learn in just a few days, and there was basically no chemistry, and there were no galaxy stars, into the complexity that we see today that led to us being here eating pizza. And obviously this means trying to answer a lot of very complicated questions, and it means that we really need to try to understand very early on in the universe what was happening. So including trying to understand how and when the very first stars and black holes formed, how they evolved, and also what kind of stellar populations were there in the first galaxies, and how essentially they influence processes which are very important, such as reionization. And obviously this cannot be done solely by conducting observations, nor solely by simulations, but obviously by trying to speak to one another and learn from the things that go well and things that do not go well, which typically is when we learn most. Now, if we think of the simplest, most fundamental measurement observationally that we can do of the universe globally, it's probably the star formation history. And this is when people look at signatures of very massive stars, which are typically very short-lived. And if you assume an IMF, and you know the volume you're serving at different redshifts, and we now know that the star formation history had a peak at around redshift 2 to 3, and it's been declining ever since. And there's a lot of interesting stuff happening from redshift 2 to the local universe, which I won't be talking in this presentation, but it's good to keep in mind that we know that the star formation rate density has been falling very quickly over the last 11 billion years, and we kind of have a few ideas of why that is, because there's less gas, because of structure formation, AGN feedback, and supernova feedback. And we also know that this decline in star formation has been accompanied by kind of a decline in the accretion rate of black holes, at least for star-forming galaxies, which means that whatever is affecting galaxies and producing less and less stars, it's also producing or giving rise to black holes accreting less and less mass per year. But I would really like to focus today is on something that happens beyond redshift 2 and all the way into kind of the epoch of reionization. So really the time of the universe where most things happen and where galaxies really assemble and form while here I think most processes happen when most of the structure, most of the metal enrichment has already been done. So it's kind of a different kind of problem. Obviously this is way more challenging because we're talking about more distant galaxies, and it's very important to always keep in mind the sort of details that for those that work in the local universe where we struggle with too much information, and when you go to the high redshift then you struggle with having only a few pixels. But it's always good to keep in mind that a lot of the results that we find or things that we discuss are kind of based on just a few pixels, and that's even with Hubble. Obviously, the other thing to keep in mind, and the reason why I'm going to use Lyman-Alpha, and I'll try to motivate it a bit more, why Lyman-Alpha emitters are actually quite important or interesting in terms of being the progenitors of a lot of galaxies we see nowadays. It's mostly to do with the fact, and for now I will completely ignore AGN, that will come back later. If we look at kind of the full spectral energy distribution within the optical and the infrareds, we can decide to study young stars or the dust that gets some of that UV light and is reprocessed in the far infrared, or emission lines with ALMA, for example, now, or all the lines in rest frame optical. Now what happens is once we go beyond redshift 2.5, and until JWST flies, or when it flies, or if it flies, and I'm going to go into those problems, is that H-alpha gets out of even the near-infrared bands, which means that whether we like it or not, and I usually get the feeling that a lot of people really have a lot of things against Lyman-Alpha. I'll try to convince you that Lyman-Alpha is not that scary as it seems. It's extremely complicated, but so are puzzles, and a lot of people like puzzles. And one of the big reasons to use Lyman-Alpha at redshifts beyond 2 is it actually gets much simpler. It redshifts into the optical band. You can do it from the ground. You no longer need very expensive observations with Hubble. It's also intrinsically the most luminous line in a star-forming galaxy. It's observationally, it's many times not that strong, but intrinsically it is. And in most cases, due to radiative transfer effects, it's very asymmetric. So sometimes to get redshifts, it's perfect. You only have a line, but you know it's Lyman-Alpha because the other lines do not show that effect. And lately, specifically coupling with other rest frame UV lines, such as carbon-3, carbon-4, nitrogen lines, you can kind of put them together to learn more about the physics of what's going on in these distant galaxies. Of course, these are the good points about Lyman-Alpha, and there's a lot of really bad points and problems with the line itself. Because being a line that very easily scatters on a neutral hydrogen, that is a problem not only within galaxies, but especially when we move into the epoch of reionization, when there's still a lot of neutral hydrogen in the intergalactic medium. But also because even within galaxies that reside now, when their reionization is complete, the escape fraction, or essentially the fraction of photons that actually make it to our telescopes, is extremely hard to measure. And this is because this scattering effect makes it also more likely for these photons to be absorbed by dust particles. And so some of the photons, they still escape, but at very low surface brightness, or very large distances, while other photons never escape because they will encounter a dust particle and they get destroyed, just like other UV photons. Now, to make progress, and before we go and survey for Lyman-Alpha emitters, I'd like to tell you about an experiment that we've conducted to really try to measure the escape fraction empirically. So in simulation, this is a complete mess. It is so complicated. But if we just take an observational approach, it's not that hard, in the sense that if we can measure the H-alpha line and H-beta to correct for dust, and using just simple case-B recombination, for every single galaxy, no matter what redshift, we can predict what should be its Lyman-Alpha luminosity. And then if we observe it, specifically if we have spatial information, we can compare it, and we can determine the actual Lyman-Alpha escape fraction. And the way we did this was by conducting this Kalima survey, and also making sure that we would cover wide enough areas with large samples and covering multiple environments to really understand if there's anything that really sets the escape fraction or if it's just pointless and we should just give up on Lyman-Alpha altogether. And the way we conducted this survey was by designing a specially built narrowband filter to get Lyman-Alpha to match with an H-alpha filter that we had already used to conduct a survey of about 5 square degrees that includes fields like Cosmos, UDS, Booties, and SA22. And then we conducted a survey in Lyman-Alpha over exactly the same areas, essentially targeting the same volume, and you have the spatial information. So you can really compare, for example, if you select a sample of H-alpha emitters that you see in the red, or if you select a sample in Lyman-Alpha emitters. First thing you may notice is, oh, same volumes, different selection, and they don't seem to sample the same population. And that is mostly because they're selecting quite different populations. H-alpha emitters are going to be the typical star-forming galaxies at redshift 2. They'll be relatively massive, evolved, they'll be dust, while Lyman-Alpha emitters are typically probing the things that have very low mass, very low metallicity, and low star formation rates. But actually, they also probe down to a much better sensitivity limit. So there are things that you can already see in Lyman-Alpha that for an H-alpha survey to get, you would need something like James Webb. Now, what you can do is, if you take all the H-alpha emitters, for example, and you stack them in Lyman-Alpha, even if they're not individually detected, you can check what is the escape fraction and visually where these photons are getting out. And this is a really nice thing to do because it was done with a 2.5 meter telescope, yet you can kind of compete with 8 or 10 meters because of the sample size and the way the experiment is conducted. So what we can do is we know where the H-alpha photons are coming from, essentially where Lyman-alpha photons have been produced, and then we can see where they're actually coming out. And as and other studies have shown, of course, H-alpha is already a bit more extended than the stellar light, but Lyman-alpha is way, way more extended. So down to the limits of the data, we do not find kind of a stop to it. And yes?
Do you have spectroscopic redshifts for these objects?
Yes.
Okay.
Yeah, so about 10 to 20% of the sample, yes. But we also, I mean, these have already been corrected for a contamination of around 10%, which is what we find overall. So there's no major problems on this. And also the fact that we see this kind of thing just in Lyman-alpha and not in the UV also show it's real line emission. Now, the other important thing to notice is that you only reveal this because you're stacking it's almost 3,000 hours of observations, because the actual escape fraction of these kind of typical star-forming galaxies is really low. It's about only 2% of Lyman-alpha photons that are predicted to have been produced actually escape within this kind of the typical apertures you'd put on a high redshift galaxy of around kind of 25 kiloparsecs. This is important to keep in mind. And we can do the same experiment if we can compare the Lyman-alpha selected sources versus the H-alpha selected sources. This is basically the same figure as we had before. And in terms of the extent, it's very similar in the sense that Lyman-alpha is still more extended than H-alpha, even for Lyman-alpha emitters. But these typically probe galaxies that are forming way less stars, and the actual normalization is completely different. So while here we're talking about kind of 2% escape fraction, here we're talking more about 30 to 40%. And actually, it's consistent with, if you extrapolate, probably almost 100% of Lyman-alpha photons escape at larger distances. So almost none of them are destroyed by dust here. A lot of them are destroyed by dust in the more typical star-forming galaxies. Now, you can also take the kind of a global measurement, and people have done this before with smaller samples, to kind of, if you look at all the star-forming galaxies by integrating luminosity functions down to this kind of 25 kiloparsecs, then it's about 5%. If you start going to larger apertures, maybe it goes to 8, maybe 10% of kind of all the Lyman-alpha photons produced in all star-forming galaxies. Only about 10% seem to ever get out, which I guess would mean that 90% are actually absorbed by dust at some point. But it's also good to keep this figure in mind in terms of what the selection means. When we look in terms of age alpha emitters, it's really low escape fraction. If you select in Lyman-Alpha, it's not surprising, of course, but the escape fraction is way higher. Now, but to use this and to use Lyman-Alpha emitters, we kind of need to calibrate on more than just Lyman-Alpha selected or age alpha selected. So we've looked at how this escape fraction may correlate with some properties, and not surprisingly, it comes out as kind of with correlation you'd expect, in the sense that if you look at galaxies that have low dust extinction, typically they have high escape fractions. Things that are bluer also have higher escape fractions, or things that are less star forming also higher. But this is where the problem really begins, is a lot of people that have tried to do this, they look at the scatter and it's just horrendous, and you can't really use a relation like this to kind of extrapolate or to predict the escape fraction. Even more so because there's subtleties like the reddest galaxies and somehow have higher escape fractions, or things that are incredibly dusty can also have quite high escape fractions, like submillimeter galaxies, which were spectroscopically confirmed using Lyman-Alpha. So the picture is not that simple in terms of if you're dusty, then you basically have no Lyman-Alpha photons escaping. So instead of just giving up, like a lot of people, we try to step back and ask ourselves if there was anything that was simple enough that would allow us to predict the Lyman-Alpha escape fraction in a better way than this. And it turns out, and we can discuss the subtleties of this, it turns out that if you just measure the Lyman-Alpha rest frame equivalent width, you can actually predict the Lyman-Alpha escape fraction, so derived from age alpha dust extinction, really well. And even more interestingly, it seems like this relation, which we kind of interpret physically and why this may be the case, seems to be the same all the way from redshift 0 to at least redshift 2.6 and maybe even redshift 5, which is really interesting. And the scatter is not really that big in terms of, given how complex radiative transfer of Lyman-Alpha photons are. And this is not just what you would expect, given that an equivalent width is kind of a ratio between Lyman-Alpha and UV. If you just use some standard prescriptions, galaxies should follow kind of this line. They do not, and these has consequences for kind of what are the properties of Lyman-Alpha emitters and their stellar populations and the fact that they can't be very dusty, etc. But what's more interesting and applicable is that you can use this relation, and the only thing you need to measure is the Lyman-Alpha rest frame equivalent width and the observed luminosity, and you can get the dust extinction star formation rate to within something very similar to any other star formation rate kind of indicator. And this seems to work at least up to redshift 5, which is really interesting. And hopefully once JWST flies and can make these measurements at high redshift, we can really test whether this is the case and really understand why does this relation that seems to be so simple works. And obviously the interesting thing about calibrating Lyman-Alpha is also as a way to measure the Lyman continuum flux of galaxies. So this is one of the most exciting parts of this calibration, is that the only thing you need to know is essentially this rest frame equivalent width and the observed Lyman-Alpha, and you can predict what should be the intrinsic Lyman continuum from these sources. I'll leave it here, and I'm more than happy to discuss with anyone that's interested about the relation for the next 3 days. Now, so far, try to convince you that Lyman-Alpha is complicated, complex, but it can be modeled, at least empirically, for star formation processes. But AGN, and specifically quasars, are actually the brightest Lyman-Alpha emitters in the universe. So for the rest of my talk, I will not, unless I explicitly say it, I will not be discriminating between Lyman-Alpha emitters that are star-forming powered versus the AGN powered. For me, a Lyman-Alpha emitter is a source that emits Lyman-Alpha. And I'm just saying this because for some people, when they talk about Lyman-Alpha emitters, they're already excluding AGN, and we're not here. Now, the other thing to really point out before moving into the surveys and the results that we found is that you can kind of distinguish between two broad ways of surveying the universe, from the very pencil beam, super deep Hubble surveys, which allow you to find the faintest things, but are very cosmic variance limited, to the things you do from the ground, where you can cover really large volumes. You can tackle cosmic variance, but then you can only see the brightest things. And there's advantages and disadvantages in each, of course. And the things that I'll be talking about are the surveys, not the ones that are typically conducted with HST, but those that kind of compare in this way to it. So a few tens, hundreds, thousands of times larger in area and also in volume to the typical search at high redshift. What I'm also going to explore is a technique, so the Narrowband Technique, which essentially relies most of the time on filters that match regions of the night sky where the OH emission is low enough that you can go very deep. And also you can cover these very large areas, and you can look for sources that are brighter in the narrowband than they are in a broadband or a continuum. So this allows you to blindly find emission lines, galaxies, over these very, very, very large volumes. And what you then do is you couple it with either photometric redshifts or the Lyman break technique to then distinguish. So you know that a galaxy is emitting and kind of line emission. You need to know what kind of line it is. And specifically for Lyman-Alpha emitters, this is the most standard technique, is you couple the emission line with a break, and you say that there is a Lyman-Alpha emitter at that specific redshift. And the approach that we've been taking is essentially, if you think of the full universe from redshifts 2 to 8, so going into the epoch of ionization, is not only taking the kind of the standard narrowband filters that people have used before, which kind of go into these OH-free regions, but also now exploring medium band filters to get surveys over even larger volumes, to calibrate those surveys by essentially having narrowband filters that match the medium band, so we can really understand if there's biases or if there's things we're missing, and also extending it to redshift higher than 7, which is an ongoing survey at the VLT. So most of what I'll talk about has been published this year, and we call this Slicing Cosmos in 4K, so this is SC4K, and you can see it as kind of a very low cost, extremely low cost IFU that essentially slices the universe in cosmic time from redshifts around 2 to 6. So if you apply this narrowband technique with all these different medium band filters and the narrowband filters there, over the full cosmos field, so this is 2 square degrees, then what you end up is with a sample of Lyman-Alpha emitters that looks a little bit like this. So you can see it in redshift and in terms of look back time. And obviously a lot of the differences in the density of sources have to do with the individual depths, which obviously we take into account. And that is also why there's so many red things here, because this data is incredibly deep. It's not because there's suddenly a superstructure in cosmos at very high redshift. The great thing about doing these surveys in fields like cosmos is that we instantly have access to all the other multi-wavelength data, including Chandra data, which we're working with this week. And also, all these samples are publicly available. So if you are interested in exploring, you can just download and use it straight away. Now, the first thing that almost everyone does when they get a very large sample of Lyman-Alpha emitters is to look at how they distribute in Lyman-Alpha luminosity, so a Lyman-Alpha luminosity function. And what you're seeing here is if you can combine the full 4,000 Lyman-Alpha emitters from redshifts 2 to 6, and you compare it with similar measurements done with MUSE and also with slit spectroscopy, this is how it looks like. So the global, you can call this the global Lyman-Alpha luminosity function. It's very, very steep. So the faint end slope is almost about -2. And you can see that the difference is by conducting these surveys over very large volumes and exploring the medium band filters, you go up to luminosities which are really, really high. And we'll go into it when we explore kind of the AGN nature of these sources. So apart from obviously getting a global Lyman-Alpha luminosity function, the great thing is you can either look at it for the individual redshift slices, or you can combine them to get even better statistics on kind of slices in redshift of about from 0.2 to 0.4. And what we can see is that although the evolution is not very strong, so from redshift 2.2 to maybe 3.1, without these very large statistics, you probably would just conclude that the luminosity function is exactly the same, but there is subtle evolution. And you can see that essentially there's a little bit of a rise in the typical number density of Lyman-Alpha emitters from redshift 2 to 3.1. And then what seems to be happening is that the typical number density goes down, but there's power kind of being transferred to the bright end, up to at least the epoch of reionization. And that may be connected with this extra component of the Lyman-Alpha luminosity function, which is very pronounced at redshift 2.2, and it kind of goes down. And as I'll show you just in a couple of minutes, this is all driven by AGN within the Lyman-Alpha emitters. So maybe still this increase in the typical luminosity could still be because there's an AGN population that's kind of contributing to it. But that's very hard to find because even the deepest observations with Chandra are not sensitive enough to find some of these sources. Now, I think what's really puzzling and interesting about all of this is the luminosity, if anything, the luminosity function is kind of positively evolving. But at the same time, we know from the UV perspective, mostly from HST surveys, that UV luminosity density is going down. I mean, the star formation rate density is going down from redshift 2 into the epoch of reionization. But somehow, the Lyman-Alpha luminosity density is actually increasing a little bit up to redshift 3 to 4, and somehow manages to stay constant. And this has to mean something in terms of the properties of galaxies. It means that you can think of obvious explanations. One is that there's just more Lyman-Alpha photons escaping from these galaxies, and probably because they're more dust poor, their metallicities are very low, maybe because they're very compact, so they're in the conditions where it's very easy for Lyman-Alpha photons to escape, or maybe there's just more Lyman-Alpha photons being produced. Again, because maybe you're looking at stellar populations that are very metal poor. So to kind of try to distinguish and understand what's going on, we looked at completely independent samples and tried to understand if in general galaxies are changing. And I think one of the strongest evidence, and before we have James Webb to really do spectroscopy and establish this on kind of UV selected and mass selected samples, I think it's very clear evidence that the typical equivalent widths of all lines are going up very, very quickly from the kind of the Sloan level up to kind of at least almost 2 orders of magnitude higher. And you can only get this if the typical kind of stellar populations are changing. And probably the best guess is that they're just way more metal poor. Typically, they're more metal poor, and that there's more kind of Lyman continuum photons being produced per UV luminosity, for example. And it's interesting because by redshift of around maybe 5 to 6, these kind of properties are the ones that people find in the local universe, but being extremely rare. So galaxies with number densities of like 10 to the minus 8, kind of this green peas and those extremely line emission line galaxies in Sloan, are the typical galaxies at redshift 5 to 6, which is something really quite interesting on how the kind of average nature have changed from the local universe to the distant past. And also independent evidence, it shows that there is likely quite a big difference in what is called the ionization efficiency of galaxies, kind of the typical ratio between the amount of Lyman continuum photons and the UV photons, or essentially how blue galaxies really are beyond the UV. And this means that we expect galaxies, when we go from redshift 2 to 6, that they will be producing more Lyman-alpha photons per UV luminosity. So it can't just be that the Lyman-alpha escape fraction is increasing. There's at least some effect of this kind of ionization efficiency. So if you model this, and if you look at the ratio between the Lyman-alpha luminosity density and the UV luminosity density, because the UV is going down, Lyman-alpha is going a little bit up and then stay constant. This is what we're seeing from redshift 2 into the epoch of ionization. It's going up by quite a lot. But our best explanation is that most of it is due to the typical escape fraction going up by quite a lot. But there's still a factor of about 2 in this psi ion, in the ionization efficiency. So partly is because galaxies intrinsically are producing more Lyman-alpha, but most of it is because galaxies have the capability of kind of letting the Lyman-alpha photons escape much more easily. So we're talking about a factor 2 from a higher Lyman continuum UV production and a factor 4 in terms of the typical Lyman-alpha escape fraction. And one of the reasons may be as well, in terms of when you look at how these galaxies look like, you probably wouldn't be surprised that as you go from the low redshift universe into the epoch of ionization, that they somehow have an easier time in terms of letting these photons escape. That's because at high redshift, essentially all galaxies are extremely compact, or the typical galaxies are very, very compact. And essentially, the typical sizes of star-forming galaxies, they converge to the sizes of Lyman-alpha emitters. So if you select galaxies by having very strong Lyman-alpha across cosmic time, they seem to all trace this kind of 1 kiloparsec size, which is probably connected with both the evolution stage and also the size, that kind of the maximum size that maybe you can have before a lot of processes start intervening in the way Lyman-alpha photons escape. And then if you're too evolved or too big, then I guess you don't detect them as Lyman-alpha emitters anymore. Now, and so far, I've been mostly talking about Lyman-alpha emitters as star-forming galaxies, and a lot of studies have been conducted to kind of try to understand what their masses. And the typical Lyman-alpha emitter is very low mass. Some of them kind of 10 to the 7 or 10 to the 8 solar masses. They're typically very low star-forming galaxies, and also typically in kind of very low in UV luminosities. And most of them, or many of them, actually completely undetected, even with HST. But if you look at the population as a whole, and specifically if you explore really large volumes, you understand that not all Lyman-alpha emitters are like this, and that there are Lyman-alpha emitters that actually extend to quite high masses, to high star formation rates, and also that can be quite bright in the UV. And this is even more so if we look at redshifts around 2. And one of the really great things about the Cosmos field and others that have Chandra data very deep and also very deep VLA data is you can very easily identify, for example, if some of these are actually being powered by AGN. And there's quite a lot of them. Given that the sample is so large, you probably obviously expected. And it turns out that depending on how you do it, about 2 to 5% of all the Lyman-alpha emitters are detected in either Chandra or in the radio. And some of the things that are detected, even though they're Lyman-alpha emitters, they're really quite powerful X-ray sources. So some of them are just your more typical quasar, accreting very, very rapidly, and some of them a few solar masses per year, while essentially 95% are completely undetected. And if you only look at those that are clear AGN, this is where this kind of pink luminosity function comes from. So you can do the Lyman-Alpha luminosity function of the pure AGN population. That is definitely not as steep, but that really extends to way larger Lyman-Alpha luminosities. And that we know from looking at which sources these are, they're actually tracing kind of really strong overdensities or kind of more protocluster environments. These are what people would call kind of the Lyman-Alpha blobs or Lyman-Alpha halos that we can just discover blindly because of the volumes that we're covering, which are kind of 10 to the 8. And the interesting thing is that this AGN component, so you can see here, that's spectroscopically confirmed. So I think almost 90% of all these have a spectroscopic redshift because, again, their X-ray sources have been targeted elsewhere. And you can see that this is there when you look at every individual slice from redshift 2.2 to about 3.3, but somehow it disappears beyond the redshift of around 4. And this could be due to a lot of factors. Maybe the AGN population just becomes even rarer, that our survey doesn't get it. Or maybe this power law component is just at the lower number density. Or maybe it's just somehow the population gets mixed up and maybe it's responsible for this kind of brightening of the Schechter components. What it's really interesting, I think, is that if you look at the sources that are X-ray detected, and if you look at how the X-ray luminosity may be related with Lyman-Alpha, you see that there's quite a nice correlation in the sense that it looks like the Lyman-Alpha luminosity is actually tracing the accretion into these supermassive black holes. So it's definitely not coming from star formation as far as we can tell, because of this, the correlation that works really nicely. And there are some trends in terms of redshift, in terms of this correlation maybe changing, and especially once we move to the high redshift, where there's way less X-ray emission for a given Lyman-Alpha emission, or maybe there's just more Lyman-Alpha emission for a fixed X-ray luminosity. And this is something we're now also working on to try to really understand what's going on, and if we can really establish if the Lyman-Alpha is really coming from the accretion disk or from kind of shocks or galaxy-wide. Now, obviously, the problem is if we just rely on X-ray or radio data, there's just the flux limit. So we have around 100 to 200 AGN within the sample of 4,000, but we may still be kind of missing some AGN Lyman-Alpha emitters. So to try to address that, we just went to KEC, VLT, and WHT to really try and get spectroscopy. So the point was to really try to look at the kind of the lowest accretion rates into black holes, or black holes with much smaller masses. And essentially by starting with the brightest Lyman-Alpha emitter and then going all the way into kind of a flux limited sample, this is how they look like in Lyman-Alpha. And the first thing you'd notice is how diverse they are globally, but also how they change from kind of your broadline AGN at the highest luminosities into things that start to show some kind of double peaks. They become narrower, and then they enter the kind of just pure star-forming regime, which are very narrow, and they have no indications of AGN activity. Now in here, you already see some of them are classed as AGN. Some of them are because they're very broad, so their full width F maximums well in excess of 1,000 kilometers per second. But for the other ones that are narrow, the way we identify them as AGN is by doing photoionization modeling and exploring the full spectra. So looking at lines such as carbon-4, helium-2, and carbon-3, and really trying to distinguish between what's powering these Lyman-Alpha emitters. And there's obviously kind of things you need to take into account, like the metallicity and other parameters. But you can definitely identify the ones that are AGN and that otherwise they kind of look like star-forming galaxies. So they will not have, or they do not have X-ray emission, they do not have radio, they're narrow line Lyman-Alpha emitters, but they have line ratios of these lines that are clearly place them into the AGN regime. And what this kind of allows you to do is to get a broader, more complete picture within, I know it is a very complicated, messy plot, but it's kind of showing the whole zoo of Lyman-Alpha emitters coming from Muse and from other narrowband surveys in terms of what is their UV luminosity, and this just compares a typical UV luminosity at those redshifts, and in terms of their Lyman-Alpha luminosity, and again, this is the typical Lyman-Alpha luminosity there. And what we find is that there's kind of this limit, so you can see projected in Lyman-Alpha here, or in UV here, where the fraction of AGN within the sample goes up very substantially, and by the brightest UV luminosities, 100% of all Lyman-Alpha emitters are AGN, and the same thing goes in terms of Lyman-Alpha luminosity. And the other thing we really wanted to point out is that if you just do an X-ray selection, you'd get the same qualitative result, but the offset here is just the things that are likely accreting below your limit, or maybe there's or the black hole mass is too low. And just for reference, the typical SDSS quasars have these kind of Lyman-Alpha luminosities, but they would kind of appear around here. So this is kind of a different population of maybe lower luminosity AGN, and I'll come back to these galaxies here that have been named at high redshift to try to interpret them. Now, one thing that comes out in terms of the physics of what that relation is telling us, that I think it's really quite interesting, is that if you look in terms of the typical, for example, Lyman-Alpha luminosity and the fraction of AGN, it essentially goes up very sharply at around 2 times kind of this knee of the luminosity function. And this is the same if you look in terms of the UV or Lyman-Alpha, which is shown just green or pink. But what it's interesting is if you look at H-alpha emitters, this fraction still goes up, but there is no sharp transition. So the way we interpret this, kind of this wall at which beyond it, if you select a Lyman-Alpha emitter, you're basically just selecting an AGN, is to do with kind of a maximal starburst before dust extinction starts to affect whatever you see coming out of the galaxy. And it turns out that it's about 20 solar masses per year, redshift 2 to 3. So at this redshift, it seems like if you're forming more than 20 solar masses per year, obviously your galaxy intrinsically will be even more luminous in the UV and Lyman-Alpha, but you will not see it as more luminous in UV or Lyman-Alpha because it's going to be obscured. And this makes kind of a wall into how luminous it may be if it is star forming. While AGN, they can produce these luminosities not through star formation, and not by kind of fabricating dust while they do it, for example, while they accrete, which means that AGN can very easily exceed this kind of maximum luminosity, and they can be observed as even higher luminosities. And this is interesting in terms of if this is kind of linked to the knee of the luminosity function, because we know that this knee kind of evolves, maybe this maximal kind of unobscured starburst also evolves to high redshift. Meaning that at high redshift, maybe instead of being 20, could go up to maybe 50 to almost 100 solar masses per year. So this is something that would be really nice to test. The other thing that you can learn, and that I think was not been done enough, is to try to connect it with something that you can probably then go into the simulations and start to talk a bit more, which is to understand in which kind of dark matter halos these Lyman-Alpha emitters reside in. And you can do this because the samples are very large, and they sample a wide range of galaxies, and you can just look at the 2-point correlation function, and we know very well what is the redshift distribution, and we can convert it into halo masses with assumptions that if you want, we could discuss in all the caveats. And typically in other studies, people have tried to kind of find one answer, so that the typical dark matter halo that hosts Lyman-Alpha emitters is X. And I think what we're finding is that there is definitely something we should not be doing, because they're hosted by a variety of dark matter halo masses. Yes, specifically depending on their UV star formation rates or UV luminosities, which means that the brightest things, which we know are primarily AGN, they're actually being hosted by quite massive dark matter halos of almost 10 to the 13, even in redshifts kind of 5 to 6, while the ones that are incredibly faint and forming maybe kind of 1 to 10 solar masses per year, they're more in halos of around 10 to the 10 to 10 to the 11. And these are the things that most studies before have focused on because they're the most numerous. And they're the things that you get when you go extremely deep. But they actually sample the entire thing. And this is important because it allows us to kind of put into perspective and understand what they're going to turn into. So if we can measure the dark matter halos that they reside at high redshifts, and then we can use simple modeling in terms of understanding what those halos will grow into. So it means that when we look at the galaxies that are way beyond or below the knee of the luminosity function, things like here, they're actually likely going to turn into kind of Magellanic Cloud galaxies. While those that are around L star or a bit below, they're the things that should turn into Milky Way galaxies, while these things are very likely to be kind of the BCG in some of the most massive clusters. And their number densities also match up quite nicely. So in a way, this allows us to look at Lyman-Alpha emitters as kind of the early phases of a range of galaxies that we see in the local universe, but at the phase where they're actively assembling their stars and black holes. So in the final minutes, I would just like to talk a bit about going into even higher redshifts, into the epoch of ionization, and what we're learning from it. And usually when we think about the most distant universe, we always say that James Webb will come and will solve everything. And unfortunately, we know that there's been some delays. I think I had this plot before, and many people have done similar things, but I guess at the moment, we're on track. Hopefully, this will go down and it will actually be launched in 2021. But even if it continues the trend, I think there's a lot that we can already learn. I guess a lot of people think we're data starved. We're not data starved at all. And even if we were to take to 2030, I think there's a lot of science that we can still do, even at the highest redshift. And that is mostly if we focus. So I'll just be talking about this kind of redshift slice at around redshift 6.6. And mostly in terms of looking at some of the brightest galaxies and some of the brightest candidates that we found. And typically the big problem and the reason why JWST will be so important is for most candidates that come out of Hubble, it's very hard to get their spectrum to confirm that they're actually at that high redshift. And the great thing about taking this kind of perspective or method of going very, very wide is that you can detect sources that are bright enough that very quickly you can confirm them spectroscopically. If you don't, it means they're definitely not at that redshift. And this means that even though we're talking about redshifts of around 7, you only need about 15 minutes and you can see the lines in the raw data, which is really cool. So this is an example of CR7, this is a Keck Demo spectra where you see the Lyman-Alpha there, and this is Cola 1 in the raw spectra of X-Shooter. So it's something that even without data reduction, you can see the line directly, even though they're such distant galaxies. And these are not quasars. I mean, you could do this for quasar-like sources, but it seems like these are relatively typical galaxies at this redshift. So it means that over the past about 3 years, we've been conducting the surveys and spectroscopically confirming all these galaxies. And we're now in the stage of really trying to understand what's going on and show that with telescopes like the VLT and ALMA, you can actually learn about the physics and the complexity that goes on within these galaxies. And this becomes really interesting once you kind of couple the power of So we use these ground-based telescopes to survey the sky, and we do the reverse. We then, with a lot of effort and with a lot of no's and rejected proposals, we finally get time on Hubble to follow it up. And this is how all these galaxies look like at redshift 7. And it's really, really booming. And the great thing as well, apart from measuring their sizes, seeing if they're mergers or not, is if you can combine it with MUSE, you can have a really nice idea spatially where Lyman-Alpha is coming from. You can look at that in 3D, which we're doing now. But you can couple it with ALMA, and you can try to understand also where any dust may be coming from, and also components within other lines, such as C+. And you can combine all this information to really learn a lot. So there's probably the things that we'll be doing routinely once JWST is launched that we can already do now with these very, very bright sources. And the extra thing you get out is, because all these sources are in the epoch of reionization, individually you can kind of conduct tests of kind of how ionized the medium is, and whether these galaxies somehow reside in kind of early ionized bubbles versus those that will not show Lyman-Alpha, because Lyman-Alpha just scatters out of the line of sight. And I won't show the details, but I just wanted to flash it in case anyone is interested in discussing this really cool galaxy that was discovered by Hu et al. In Hawaii, but that we followed up with X-Shooter, because we were really convinced that this was a No2 emitter, because no way a galaxy at redshift 7 could have a double peak Lyman-Alpha emission, but it really is there. It's really at this redshift. And the best way we can use to explain it is that it really is a galaxy that has kind of ionized its own bubble, and that the IGM is transparent enough that not only can we see kind of the entirety of the red wing, that we can actually also see the red wing, the blue components. And this is really cool if we find more of these examples where we can advance our understanding of the reionization process even before things like SKA. So for the final minutes, 5? Or, yeah, okay. I'd just like to talk about what we know about the nature of these galaxies, and specifically on the case of Cosmos Redshift 7, CR7, which has sparked a lot of debate and controversy and a lot of papers. And I just brought this plot back because at redshift 2 to 3, we know that anything within kind of these luminosities in UV or Lyman-Alpha, they're 100% AGN. Yet at these redshifts around 6 or 7, there's a lot of sources that we're finding with the same kind of luminosities where we don't have any clear indication that they are AGN. So they're very narrow in Lyman-Alpha, but at the same time, there are indications that they could have these kind of high ionization lines. It's just very challenging to get down to the depth necessary to really show whether they're AGN or maybe they're being powered by kind of binary populations that can also give rise. And this has not only been found in Lyman-Alpha emitters, but it's been found in Lyman break galaxies. It's kind of evidence that galaxies within the epoch of reionization have kind of very hard spectra. They show lines that in the local universe are extremely rare, but somehow they become more predominant at this epoch. And I think the really important thing to point out is that in galaxies that are this bright, once we look at them with HST, we actually understand that they're not just a single component. So they're made of multiple UV components that likely have a different nature, maybe a different ionizing source, and maybe different metallicities. In the case of CR7, this is really important because the helium-2 line, as far as we can tell at the moment, without further observations, it's actually coming either in between the clumps or it's actually not coming from the brightest UV clump. And this has consequences in terms of maybe there is an AGN there that's contributing to the total flux, but it really matters in terms of discussing when we talk about galaxy X, do we mean this clump, or that clump? And I know this is incredibly complex, but this is reality because when people have followed these up with HST, almost all of them show these multiple clump morphology showing kind of different colors and indications that they really are different. And if they're kind of assembling galaxies, they're merging, some of them could have kind of a supermassive black hole that specifically with the merging can accrete a lot. So I think I'll just show the kind of what the things you can learn from galaxies like these, and specifically for the case of CR7, if you can combine information from Hubble, which is the background here, where we know there's these 3 UV clumps, with Lyman-Alpha showing that it really extends over those 3. And in ALMA, we do not detect dust, but we detect C2, and we know it actually covers the entire system. And at the same time, with ALMA, you can get a 3D view, and you can really show that this galaxy, if we were to observe it at low resolution, maybe people could claim that it's a rotating disk. It is definitely not a rotating disk. It is a merging system. And you can tell it very clearly here. And you can identify the different clumps that are contributing to the different velocities. And we can identify that the largest dynamical mass seems to be on top of the brightest UV clump. That's something like a few times 10 to the 10. That the other UV clump, that's the second brightest, if anything, has a quite low mass dynamically. And that somehow there's something around here that's almost as massive as this, that is completely invisible in the UV. So the bottom line is that with just this example, where we already studied to quite good depth, we know that a single galaxy, as we can tell, as one single Lyman-Alpha halo, there's these 3 different components in the UV. There's 4 different components in C2, and they seem to all have a different nature, slightly different metallicities. This component here seems to be much more metal poor than this one. And we're clearly seeing kind of a very nice example of what's likely a central galaxy during its first episode of assembling. So kind of different satellite galaxies likely coming in and forming a much larger galaxy. And we're likely seeing kind of a progenitor of a galaxy, a big elliptical galaxy that will be sitting in one of the massive clusters in the local universe. And in kind of the real data, this is how it looks like. And this is even before JWST. So I think what will be really cool once it flies is with the IFU, we'll be able to really look into these systems with rest frame optical lines, and we'll probably get even more surprise of the complexity of what's going on. And that if, for example, these 2 galaxies are merging, if they both have black holes, they'll probably provide quite a spectacular picture. So I know I've run out of time, so I'll just leave you with the take-home messages, and more than happy to take questions. Thanks.
Questions for David?
How do you handle when situations where the narrowband filter may only partially cover a line? And how do you identify those situations?
Yeah, it's a good question. So in terms of deriving luminosity functions, what we do is we just do simulations where we throw lines at a variety of redshifts. And that means that you need to apply corrections. So typically you never get the 100%, especially if the filter is a Gaussian, because there's only a limited volume where it hits 100%. So you do need to make corrections. So individually, there's an error in the luminosity. And that we can correct very well for any statistical study. For a 1-by-1 galaxy, we have that uncertainty until we get the spectroscopic redshift. And then we can really use the filter transmission, and we know what is its exact luminosity.
Given the sort of redshift evolution of things like psi-ion, dust fractions, AGN contribution to emission line luminosities, can you give a sort of bird's eye view on the systematic error in star formation rates derived from emission line luminosities? Does that change as a function of redshift?
I guess things will likely get easier at high redshift just because, well, if you have a good handle on the assumptions, just because the variety of things or star formation histories are more limited, just because you have less time. I think it matters a lot in terms of if you start thinking about having different bursts, or specifically if you look at the comparison between, for example, UV star formation rates and emission line star formation rates. They will likely start to deviate more at high redshift, just because probably everything's in a kind of a very short burst. But I would think that the question depends on whether you think in terms of absolute terms or in terms of what is the best thing we can do at the moment. And if you think of the best thing we can do at the moment, I would argue that emission lines are the best, just because they give you the instantaneous thing. You do not have to assume the constant 100 million year star formation history, which at high redshift has to be wrong. Right? So all the UV star formation rates that we just use, they have the assumption that the star formation history is constant over 100 million years, which at redshift 6, I mean, it's very hard to think that for the majority of galaxies that will hold. So I guess depends on how much you worry about kind of 0.3 dex to 0.5 dex, or I think that would be on those levels. But I think we need JWST. We need H alpha at high redshift to really start to tell.
Other questions?
Yeah, so thinking specifically about these very high redshift sources like Halo 1 with the double peak, are you sensitive enough in these wide area surveys to look for other Lyman-Alpha emitters in the same region? So I mean, the question is really, does these things, if they are in ionized bubbles, there should be other Lyman-Alpha emitters nearby. So if you, a sensitivity level, you think you could see the other sources there too?
Yeah, so we are now with Muse. So what we're doing also is the follow-up that goes way deeper around these sources. But so far, we do not find any other Lyman-Alpha emitters around them, but we find other C2 emitters around them. And which I don't know what it means yet. This is kind of very recent results. But there seems to be an overdensity of sources, but that is not seen in Lyman-Alpha. Or maybe not, well, not to the depth that we have at the moment. But I think so in the case of, for example, Cola 1, given the measurements we have, that source by itself is enough to do the bubble. But in other cases, that is not true. So I think for other cases, I guess if you see evidence that there's an ionized bubble, the source is not enough to do it, and then you do not see any other galaxies, then I guess it's really puzzling what's going on.
So just as a reminder, David will be here until Friday, so if you have additional questions, we can arrange to. Okay. Let's thank him again.